Okay, so maybe we can start now. I should switch off the. So yesterday we already see that how to obtain this single particle universe. And definitely from experiment, you got this one, this in the middle, and then from different approach, you can calculate the single particle universe. And then you will notice that this is for 9208. 9208 is so a kind of double magic nuclear. Double magic nuclear, then you don't worry about pairing correlation and so on. This is simply a mean field calculation. Then you can get this single particle number. And then, of course, always 9208 is used in the constraint of the density function. So somehow that we would like to see what is the predict power, how it would be used to predict the something we don't know. So one of these possible ways you see this tin 132. Tin 132 is the radioactive neutron-richest double magic nuclear, which has been observed so far. Because you know that if you see the nuclear chart, there are, you know that only these 5 nuclear are double magic nuclear. This is helium 4, oxygen 16, calcium 40, calcium 48, and 928. That's the so-called stable double magic nuclear. And this stable double magic nuclear are normally spherical, and they are particularly stable in comparison with their neighbors. And in particularly, this nuclear has been used quite a lot or quite often in this constraint of this nuclear. And then you see that by combining with this traditional magic number, we will have this neutron deficient double magic nuclear, like nickel 48, nickel 50, and also 56, tin 100. And then this is neutron rich double magic nickel 78 and tin 132, as well as calcium 78. And then you will see this is the double magic nuclear either on the neutron deficient side or the neutron rich side. So yesterday, some students asked about the how to measure the single particle number. So you will see there are several experimental efforts try to find, for example, the single particle number. Then in such a way, we can tell whether far away from the stability line, this magic nuclei are still there. So for example, this is tin alpha tin reaction. And then from this reaction, it was suggested that the tin 132 is not so magic. And then using this deeping reaction, it was revealed for the first time that this nuclear are still a double magic nuclear. So it's very interesting to understand whether this T132 is still the double magic nuclear. And in particularly, after we have done this calculation without without fitting to this nuclear. So it's very interesting to see how this nuclear, whether they're still doubling magic nuclear. So how to tell this doubling magic nuclear or not? And the beginning of this lecture, we already see there's different approach to tell whether they're still doubling magic nuclear. So what we could plot in is that simply from the bending energy, we can plot in the 2 neutron separation energy for the tin stop chain, or we plot the 2 proton separation energy for the n equal 82 isotonic chain. Then you will see, you will be surprised to find that, for example, this star represents the experimental values. So you could see in both sides here. So the good point is that both the 2 proton separation energy and 2 neutron separation energy data could be well reproduced by all the relativity density function. And that simply told us that get the spin of the splitting automatically is really good. So we can see, you see, if we plotting again the same spectrum as 908, but the different thing is that we plotting the neutron single particle level for tin 132. So you will find that the experimental value, this side is relativistic approach. This side is the Scum density function. Then you will find the relativistically the predicted power is really satisfactory, right? So from this data, you will see more or less the experimental one much more reproduces the data. But if you do done that, even in this Scum density function, you will see in most of the case, in particularly this level, 2F7 half is differs. And then we can also go back to the 60s. You will see this is the so-called phenomenological Nielsen models. And as we all know that this model is very successful, essentially is a deformed harmonic oscillator. And on top of the deformed harmonic oscillator, of course, they have added a spin orbit term, and this is R square term. This is 2 parameter in this Nielsen model. And this C and this is the coefficients kappa and mu that is in the Nielsen model. Or in other way, the people always also call the C and the D, right? So you will see that if you see this is for T132, this is the experimental value, and then this is all present work, and this is a refitting of the new parameter side, new Nielsen parameter. This is traditional Nielsen parameters. So this figure simply told us that when you're talking about the magic number far away from the stability line, it's better to trust this relativistic approach, right? So then, of course, to help the people in this who still use this, for example, Nielsen model, we also using the present relativity density function to provide the new Nielsen parameters. And then you see this is a new Nielsen parameter. This is a traditional one. This from various density relativity density function we give the coefficients, how they change with z numbers. This is a traditional Nielsen model, you will see they have different trend, and this expand the values. And then again for the as a function of the proton number, you will see that is the traditional Nielsen parameter, and this is the data told us, and this is how the relativity density function approach the data. So you see, even though we don't including the single particle level when we building the relativistic density function, but still what we obtained is really intelligence. And the single particle level you see, if you extract it from the data, it could agree. Therefore, we can go step further. And as I mentioned yesterday, there are a lot of applications. And at the beginning, I so to say, try to cover as much as possible. For example, the ground state property, and apart from the Schroeder spin symmetry, mass, and radius, and so on, then we go to the excitation energy. That means rotational excitation, vibration, and then we also, so to say, interface with the other fields like astrophysics or the standard model, because nowadays, for example, the neutrality double beta decay is also very interesting topic. So from the relativity density functional, there are also a lot of work going in such a way. But since it's officially this is already the last one of this series of lecture, maybe I just choose several of this topic. We will see. For example, tomorrow we also continue a little bit of the lecture. Apart from what the question you have already collected, I wonder how many questions has been collected. Still, oh, you will do that today. Okay, fine. So we will see that, for example, that now we were talking about Schroeder spin symmetry and spin symmetry, right? So the Schroeder spin symmetry and spin symmetry, this is, so to say, the ground state property. Of course, you see from the density function now we have built up. In principle, we already can describe all the ground state property. For example, the ReD, the single particle level, total bending energy, the neutron separation energy, size, the dimensions, for example, the magnetic moment, and so on. All of them could be described well, or in principle, they should do this work. And then from the single particle level, so to say, we will try to understand the Schroeder spin symmetry. You have already seen this figure several times, right? And you also already know the story of the Schroeder spin symmetry. And this is a good way, follow the trend of the development of science and go perpendicularly to the mainstream. That's the experience from some senior scientists, that how you can find something different. I suppose this idea of the Schroeder spin symmetry is exactly the same thing, because at that time the shear model is really the mainstream of the nuclear physics. But they try to find something totally different from the traditional shear model. That is Schroeder spin symmetry. So okay, so now we will see what can we do, right? We already mentioned that from the Dirac equation in the spherical case, then the wave function for the Dirac nucleons could be written in such a way, right? This is up components and this is no components. Here you see we have factor 1 over r here, and we have also different sign for the up and no components. This is not this is not that difficult to understand. You can simply assume up component and no components. And finally, you will see if you're writing the wave function in such a way, the individual equation will be much more simplified. And then the important thing is that the quantum number here. For the radial part, we have n and kappa. N is so-called the node number plus 1 for the radial wave function. If they have 0 loads, their load, then the load number is 0, then n equal 1. Otherwise, simply plus 1. Kappa is the neighboring of the orbit angular momentum and total angular momentum. And then you will see this, we have, for the angular part, we have L for the orbit angular momentum of the up components, and L tilted for the low components. And then this is the relation. So the total angular momentum is always J plus or minus 1/2. And the kappa represents the combination of L and J. It could have different signs, so this is enabling a good way to remember the L and J. And L tilted is related to the orbit angular momentum in such a way, right? So you will find, for example, for the up components, if they have 2s1/2, 1d3/2, then both of them will have the low components with angular momentum p1/2 and p3/2. So essentially, this is a kind of pseudo orbit partners, right? And then if you compare these pseudo orbit partners, you will see what is the difference of their components. So we could conclude that the pseudo orbit angle pseudo quantum number are nothing but the quantum number of the low components, right? Then we can do a little bit of mathematics. The simple way is that from the Dirac equation previously, we will see this is the coupled differential equation. And then we can reduce easy or remove easy the up components or the low components. This is a simple mathematics exercise. And then you will end up, for example, the Schrödinger equation for the up components and low components. I call it Schrödinger equation because you will see in the denominator, it is much more complicated. Because you see we introduce, for example, this effective mass here. In this effective mass, which appears in some of this denominator, they also contain the eigenvalue. So it's not a simple Schrödinger equation. So we call it Schrödinger equation. But if you're looking at this equation, for example, you will find that, for example, for the up components, right? If we don't have this term, because this term, we have the kappa here. If we remove this term, then you will see the eigenvalue has nothing to do with the spin, right? So we have spin symmetry. And then how to make that if this derivative is valuish? We will have spin symmetry for the nuclear state. And then for the low components, again, if we remove this term, kappa tilted, then you will see this L tilted, the energy only depending on the L tilted. That means pseudo orbit partner will be degenerate. That is a pseudo spin symmetry we are talking about. So this is for the nuclear part. And then what about the antinucleons? Antinucleons, if we do this charge conjugate of take the charge conjugate of the Dirac equation, then we end up with the equation for the antinucleons. So in this antinucleons, we will find that, for example, here, this the small components for the particle case become the up components for the antiparticle, and also the up components for the particle become the low components of the antiparticles. And then for the antiparticle, you will see in this term, this is the term which broken the spin symmetry, right? So if this term vanishes, we will have a spin symmetry for the antinucleons. And if these terms vanish, we will also have pseudo spin symmetry for the antinucleons. That's interesting because experimentally we do measure the single particle levels for the proton and the neutron, but nobody has seen the single particle level for the antiproton and antineutrons, right? Anyhow, this is interesting, and also if you look carefully, you will find for the nuclear, you see for nuclear, the small components is this. This is how, if you neglect this term, this is how they broken the pseudo spin symmetry. And for the antinuclear, this is this term which broken the spin symmetry for the antinucleons. And then you will find that this factor for the antinucleons is about 400 times smaller than for the nucleons. So in such a way, you will expect that the spin symmetry in antinuclear spectrum is even better. The question comes, because we don't know yet, we don't. Have you ever, any of you have tried to look into the Dirac sea? So that is a good question, because 20 years ago, nobody has looked into that Dirac sea. We try to ask these people who are interested in antimatters. Then we try to ask them, do they have any experience about anti-nuclear inside the nuclear, how the Dirac sea looked like? And then, the most authoritative response we get is that there are meanings of levels in the Dirac sea. So since the meanings of level in the Dirac sea doesn't make sense, because you cannot plot meanings of single particle level in the Dirac sea. If you trust this, then you are wrong. So we simply plotted out the Dirac sea. So for example, this is oxygen 16, because we have scalar potential and vector potential, right? So we can plot out, this is the neutron potential for the neutrons. Simultaneously, we're also plotting the potential for the anti-neutrons. And then we plot out how the anti-neutron level looked like in the Dirac sea. So you will find that, there are around 10 level for oxygen 16 for the neutrons. Then about hundreds levels for the anti-neutrons, not millions of them. Hundreds we can still handle. So we plotting the level for the anti-neutron in such a way. We plotting the figure in such a way. You see, because the level is really more than that in normal neutron level, So we're plotting, this is S, this is P1 half and P3 half, and then D3 half, D5 half, F5 half, F7 half, G7 half, and also G9 half, and H9 half, and H11 half, and so on. So that's how we plotting this figure. And then if you check carefully, you will find the spin orbit splitting for the antineutrons is much smaller than the splitting in the neutron single particle level. So this is very interesting because we suppose underneath that theoretically we can understand much better how the antineutrons sitting in the nucleus theoretically. And then experimentally, of course, it's very difficult. If you have anti-neutron here, immediately they are annihilated with the neutrons, right? So how to prove the existence of this Dirac sea? Do you have any idea? And then last year, I gave a talk for the people from heaven-ion collisions. It's a pity that, nowadays even all of us are doing nuclear physics, but we are divided by some boundary. For example, the people working in heaven-ion collision, people working on field body, main body, experimental theory, and reaction and structure, astrophysics. So we didn't talk so much with each other. And then I showed them this figure. If you believe in Dirac, this Dirac equation must be correct. Then, because we already know quite a lot about the nuclear property from the Dirac equation, then this Dirac equation told us there should be a such Dirac sea, right? So we have enough reason to believe that this Dirac sea is correct. Perhaps also even the single particle level that should exist. But the question is that we cannot put in anti-neutrons. So there is possibility that, but some of you are studying hypernuclear, right? If I remember correctly, some of you are working on hypernuclear. We can definitely also put hypernuclear here. But hypernuclear doesn't help us so much to explore the Dirac sea. So what we need is putting anti-hyperons. For example, anti-lambda. Why not? So we try to investigate this system in such a way, we explore the Dirac equation with lambda very easily. With lambda, we can reproduce quite well all the lambda separation energy and the spin orbit splitting for lambda particles. And then all of this is data. But then what about we put in anti-lambda? And if we put in anti-lambda, we have something similar as this figure. So it's quite interesting. And at least we could prove that how the Dirac sea looked like in the nucleus. And then, fortunately, we have a hope. The hope is that any experimental group from Rick Star collaboration, they told me they have bombarding gold against gold and they're collecting a lot of data. So if they look into the data, they could have a chance. They already, from that data, they already found, for example, helium-4, anti-helium, and so on. But all of that you see, they have matter and antimatter separately. Now, if we have anti-lambda here, that would be something different. because we have really matter and antimatter mixture. You see, that is their way they bombarding each two nuclear, for example, gold to gold. And then because the energy is so high, in principle, they open all the channel. So they should have, matter and antimatter there. The only difference is that even though it was produced, how can they distinguish this is this this is the object they are searching for? They also found anti-helium. They published a couple of years ago in Nature or Science, and they even found that they found the interaction between antiproton and antiproton. But that is trivial because essentially that is a big story, but essentially the same. Antiproton interaction is similar as proton and proton interaction. Yeah, this is a story that we try to mix antiproton with nuclear. Because I haven't heard the this is the story here because I have oxygen 16 here. This is neutron single particle level for oxygen 16. So essentially, you have s orbital p3 half, p1 half, because you only have 8 neutrons. And then if we trust, this is the output from the Dirac equation, right? So if we trust Dirac equation also provides us this, so to say, Dirac C. This Dirac C is nothing but, the corresponding to anti-neutrons, right? So the only thing is this is anti-neutron, but experimentally, how can we verify that this is correct? Right? But an anti-nucleon is a hole in the Dirac C. I think I produce a hole in the Dirac C. You see, this is a different way that we put in such a way that in principle, the Dirac C, if you see all of them are neutrons, then below this is the neutron potential that should exist in a Dirac C there. But then that so to say, this Dirac C is so fancy. The people say, okay, that is corresponding to the kind of anti-neutrons, antiparticles. So that is how this antiparticle comes out. Yeah. I don't understand what experimentally is measured. Experimentally, that because that is also my understanding at the beginning. My understanding at the beginning is that we have oxygen here. Can we put in some anti-lambda? But this is proved very difficult. And then they told me their way is different because they have a gold colliding with gold. And then with the energy, they could have all kind of energy. They even told me that strategy. If energy is too high, nothing exists, not even nucleus, because bombarding gold and gold, finally you will end up with, plasma. They are talking about GEV. So for instance. Yeah, exactly. And then if under no energy, then of course the nucleus survived. But the threshold to produce hyperion or anti-hyperion is not open yet. So they told me that they have data there. They have enough data between the window to produce haploid, anti-haploid, and also the window to the nuclear disappear. To prove that, in order to guarantee there is no mistakes for them this is also new. I told them this story. As a theoretician, I trust my theory. So as I propose this good way to verify that antimatter and matter could coexist. And then not all of the experimentalists trust me, because this is something, you might find nothing. But this guy, they found that is worth try. If they do see that, then, just before Christmas, they told me that they're searching for their data there. I just wonder, because before I suppose maybe they should write a proposal and do some experiment, and I said, no, because they already have enough data collect, existing there. The only thing is that they want to see if they do find, for example, antinumda sitting in helium-4, for example, what would be the signal to test? So that is the information I have at the moment. But this is fancy. I cannot expect it that immediately you will get it. But I simply told you that is interesting, and if I trust this story, then that is the prediction it will have. Okay. Then, of course, apart from that, a lot of work's going on. I cannot go on forever. But for example, there are also a lot of work try to study the pseudo spin symmetry in resonance. Then in order to study resonance, you have to develop a new approach, right? For example, this complex scanning method, that's how to identify the resonance from the Rayleigh-Shue continuum. And then there is also a kind of a way that for example, in the continuum, the Jost function, the 0 point of the Jost function is equivalent to resonance. There are also a lot of work along this way. And then you can also even do that, for example, with similarity normalization group and so on. Then you can easily extend it this formalism to study the pseudo spin symmetry in spherical nuclei, deformed nuclei, even triaxial nucleus. And so you see, this is the pseudo spin symmetry in the deformed case, and this is how the Dirac sea looked like for the antineutrons. And then there are also a lot of questions arise. For example, the question is this pseudo spin symmetry perturbatively or not? And because there are a lot of work, for example, in the spin symmetry, the people write that the spin symmetry is perturbative in nature, but the pseudo spin symmetry is dynamic, so cannot be viewed in a perturbative way. There are also, a lot of people agree with this idea. So then one of my students, not only one, but 2 or 3, and then they try to understand whether this pseudo spin symmetry could be perturbative. The thing is so easy because they adopted the idea of the explorer, the pseudo spin symmetry breaking by combining this SUSE, this supersymmetry, and also the perturbation theory and similarity normalization group. And then finally, they prove that, for example, they use the pseudo supersymmetry, they rewrite the Hamiltonian in such a way, and then they try to find where the exact pseudo spin symmetry exists, and then how perturbatively we can put in the perturbation, and finally we can lead to the the short spin symmetry. So I suppose that is a lot of work in this short spin symmetry. The good point is that, for example, this is the pure perturbation nature, how this symmetry could be done. So yeah, this is the case of the short spin symmetry in nature. So in such a way, we finally found the conclusion that the nature of short spin symmetry is indeed perturbative. And the only difference is that where is the symmetry limit? And in particularly, I found this short spin symmetry is interesting also for the students, because even for smart undergraduate students, they can easily handling this concept. And because simply from the solution of the Dirac equation, you can apply a lot of physics. So that is an interesting part. So maybe we make a stop here, and then we coming back for the mass and ready, and then we discuss about the Hano phenomenon. So did any of you have a question, or you want to put all of your question for tomorrow? Okay, maybe we take a break. Yeah. Coming back, and after examining the single particle level, then we go to the other properties. So the important thing, for example, the mass and radius are the most important one. And then mass and the radius, we already know, for example, it could told us about the information of the halo. And you know that it also told us, for example, the modification of the magic number. We also found could investigate the new radioactivity, and we can study for example, from the nuclear size, we can know the halo and the skin, and also deformation coupling, clustering, and so on. So this is the mass, and the radius could provide us the information. And then you see that in particularly from this night nuclear, there are already some information. For example, in which nuclear the Hano phenomena exist. And then experimentally, as I mentioned in the first or in the second lecture, when the people searching for the Hano, the experimental signal is very clear. They try to find the nuclear size and how it is depending on. This is this is not that easy, because the size can tell us whether it's Hano or not, only in a relative way, not in absolute scale. And then for theoretician as well. So that is also the time when I studied to learn the relativistic mean field. So we should see, for example, if we have a Hano phenomenon, what is the feature of the Hano nucleus? Experimentally, of course, it's clear that the size is extremely larger than the neighboring nucleus, or deviated from the empirical law. But theoretically, what could be different from the stable nucleus? And there are several things, of course, later on when maybe the people, after we learn more, then we can tell much more. First of all of these nuclei are weakly bound, because they are far away from the stability line, they are extremely unstable, so they are very weakly bound. And then because they are large in size, so they are larger spatial extensions. And then because they are so weakly bound, normally the contribution of the continuum become essential. So schematically, you could see this is a kind of stable nuclear. So you have either the proton and neutron Fermi surface, which are far away from the threshold. Normally, we're talking about 8 MeV per nucleus. But if we are approaching the drip line, for example, this is the case of the neutron drip line, that means the nucleus are so close to the threshold. And then they could have virtual scattering between the bound state and the continuum. So this kind of sense should be taken into account, right? So in order to achieve a self-consistent description of this henonuclear, so we found that we must be able to treat the weakly bound states. And we also have to include the contribution from the continuum, and we should allow a large spatial distribution. And then, of course, as far as we can also take into account the different deformation and so on. So in order to do that, we must have, in order to coupling this continuum and also the bound states, then one possible way is that we take into account the Penning correlation, right? We take into account the Penning correlation. And then in order to take into account the continuum, we should solve the equation of motion in a large coordinate space. In such a way, the harmonic oscillator doesn't work. So we should have something such as, coordinate space. So after taking into account the Penning correlation, of course, mathematically, you can prove that after you quantize the Meson field and so on, then you end up with the Dirac equation. The Dirac equation is extension of the Prevost density functional, because essentially you have the particle channel and the whole channel, and then you have the Penning channels. So you essentially double the dimension of the Dirac equation. And then you see here you have Dirac Hamiltonian, and this delta is so-called the Penning potential. Yesterday, Nicolas Schenck has already told us that this Penning potential is connected with the Penning interaction and the Penning tensor. And then for the Penning interaction, of course, normally we can use, for example, from the relativistic interaction, but then you will find that since in the normal or traditional relativistic density functional, the Fock term has been neglected. So the interaction is too strong. So one could use, for example, adopted this scum type, the zero range Penning interactions. And then after you take into account this, finally you end up with, again, to solve this kind of coupled differential integral equations. This kind of equation, if you use zero range Penning interaction, this Penning tensor is that function. The Penning force is a that function, then immediately they will reduce to a differential equation. And then differential equation, again, you can use for example, the techniques we introduced yesterday by shooting approach, by longitudinal algorithm, you can solve this equation. And then after they solve this equation, for example, this is a traditional Hano-Nishum 11. And then you will see that, for example, they have 3 protons. So 3 protons is easily to identify where they sit, because you have two protons in the s1/2 orbital and another proton in the p3 half. And then for the lithium-11, you have 8 neutrons, so the s orbital is occupied. Then the next 6 neutrons, you are sitting, though in traditionally they are sitting in the p3 half and p1 half. But in lithium's 11 case, because they are so close to the threshold, so the s1/2 orbital in the continuum could be coupling to these bound states. In such a way, immediately you will find that this s orbit, because they are sitting in the continuum, they doesn't contribute to the bending, but they contribute quite a lot to the size. So immediately you will find that the neutron density distribution is extended very far away compared with the lithium-9. That's why we could, so to say, find the halo in lithium isotopes. So in such a way, you could say that take into account the contribution from the continuum properly, then we can expect it that we can describe also the unstable nuclear quite well. And then we can extend this idea further. For example, this is for zirconium-134. You see this, because we solve the equation of motion in coordinate space, we can solve this equation with spherical box. And then that if we extended the size of the box from 15 Fermi to 30 Fermi, so gradually you could see we could describe well the extended spatial distribution of the neutron densities. So you will find this density extended very far compared with the protons, because in this nuclear we have only 40 protons, but we have 94 neutrons. These 94 neutrons you will see extended very far. This is kind of a halo we are talking about, because this is logarithm scale, and this density, even though you could sizable contribution, but extremely low in density. So this is the halo we are talking about. In this low figure, how do we plot this figure? This is the ready, and this is the density of each orbital divided by the total density. In such a way, you could see, you immediately identify which orbital contribute to the tail part of the neutron density. Not surprisingly, you will see in lithium-134, p3 half, 3p3 half, and 3p1 half are the main components which contribute to the tail part of the neutron density. This is also natural, because if you have an orbital with large orbital angular momentum, then you will have a big centrifugal barrier. This big centrifugal barrier will hint the extension of the density. So therefore, when you're talking about the halo, for example, you're talking about the halo in proton-rich nuclei, you must be careful, because you have to examine what is the Coulomb barrier. If you're talking about which orbital contribute to the halo, then you also have to tell us what is kind of the role the centrifugal barrier is playing. And then, okay, you can extend this. For example, we extended this calculation for all the proton magic nuclei. Then you will find something interesting. The most interesting thing is that for the medium or heavy mass region, For example, this is a calcium isotope chain. So, and this is the zirconium isotope chain. So when you're approaching the, the tripline, you will find this is a 2 neutron separation energy, the 2 neutron separation energy approaching zero, but almost parallel with 0 line. That means when we go to this nucleus, when we go to the triplines, a lot of nuclei may exist, but with very small separation energy. So in such a case, so we're talking about, for example, the halo could be not only be formed by 1 neutron, 2 neutron. For example, in this nucleus, there could be many neutrons. So that is the name we invented for this nucleus. This is the giant halo phenomenon, right? This is so-called the giant halo phenomenon. And then if you see the root mean square radius, for example, if you see the root mean square radius, you see we plotted the root mean square radius as a function of neutron number from oxygen to night 108. From this figure, you can see something very interesting. Because generally, with the increasing of the neutron number, this line is n to the 1/3, right? So more or less, even though their proton number is different, but changing with the neutron number. So at the beginning, we see, okay, this is the empirical law that the nuclear size follows the a to the 1/3 or n to the 1/3. This is still true, even though you belong to different isotope chain. But if you plot out the neutron radius as a function of the neutron number, more or less follow this line, right? So generally, in general, this is correct. But there are also differences. You will see the difference appear here. For example, for the calcium isotope chain here, you could see an up bending, and also in zirconium here, that's a strong up bend. So this kind of a bend here, and for the tin is nice pronounced, but the zirconium and the calcium is much more pronounced. So in such a case, it simply told us that there must be something special happening there, right? There must be something special happening there. And okay, we can also extend this game further. And for example, we extended this calculation for the whole nuclear chart. And then, of course, in this calculation, we assume all this nuclei are spherical. In such a way, we can save much more time, but we could have a general idea how the continuum influences the boundary of the nuclear chart. Surprisingly, you will see this is the tripline predicted by different approach. So we found that after including the continuum, the nuclear chart could be extended much further. How large is that? You could say, for example, this is the present, the horizontal line is the so-called atomic number, and then this vertical line show how many isotopes exist for each atomic numbers. And then you see there are different color. This color means what we have observed. And this color means, this is the region where the vicinity like F-RIP could be expected to found. It's very, so to say, optimistic estimate. And then this is the other approach, other model. This is after you including the continuum. So you will see the nuclear charge expanded by something like more than 20%. And this result has been appeared in this atomic data and nuclear data table. So if you want to have a general feature and how this, you can go to this mass table for the. And then you see this is also the figure which I show. For example, we can replace if we put in a non-hypernucleus for this tryptophan nuclear, because for the hyperon, they added more attraction for the system. So normally hyperon always extended the tryptophan. And then of course, if you have more and more hyperons in the nuclear, right? Now there's already a lot of case for the 2 lambda hypernuclear. If you have 3 lambda hypernuclear, immediately you will find you will have hyperon halos. Why? Because if you have 1 or 2 lambdas, all of them must sit in the S1 half orbit. But if you have 3 hyperons, 3 lambdas, one of them will sit in the P3 half or P1 half orbit. The P orbit will be much more weakly bound than the S orbit. Then you could see something like the hyperon halos. Then the question comes, because so far, in most of the halo I told you before is assumed to be spherical. Why the deformation in the halo could coexist is a big question. There are already a lot of discussion. They argue that this halo or deformed halo doesn't exist, right? There are already a lot of discussion. The people do some estimation or some, phenomenological model. They discuss whether, they exist or not. Since we are working in a microscopic approach, so it's quite natural. Perhaps we should extend it, the theoretical framework for the deformed case. This is not so easy. And in the beginning, we should, so to say, we try to see, okay, why don't we solve the equation of motion for the deformed case in the coordinate space? And we spend something like more than 5 years on that, didn't work. Finally, we found that maybe it's much easier if we have Wu-Saxon basis. If we have Wu-Saxon basis, then we could avoid the difficulty in coordinate space. And then using Wu-Saxon basis, we can use the Schrödinger equation with Wu-Saxon potential and use that solution as a basis. But we can also directly solve the Dirac equation with Wu-Saxon potential using the Dirac solution as the basis. You see, we are very careful people. Therefore, we use both bases simultaneously. We use Dirac solution as a basis and Wu-Saxon basis, Schrödinger solution as a basis as well. And then immediately, because underneath, we can test that for spherical case. With Schrödinger equation, immediately we found good solution. But if we study with Dirac equation, we end up with problem. The problem is that because we take only the solution of the positive energy solution of the Dirac equation as a basis, then we found that the result is not correct. And then we realized that we have to take the complete solution of the Dirac equation, including both the positive energy solution and negative energy solution, then we achieve the same results. So in such a way, that's how we gradually learn the Dirac sea. So only after we made mistakes, we know how to do that correctly. Then for the deformed case, what we do is that we use the solution of the Dirac equation, and then we expanded the wave function of the deformed case in terms of Wu-Saxon basis, right? And then this Wu-Saxon basis is spherical, that is expansions. And the Dirac basis, you could see we could solve that by in coordinate space, and then use that numerically as a basis to solve the equation. And then you see when we expanded the wave function in terms of this spherical case, we must be very careful how many terms we should take into account, or what is the cutoff energy. But I mean, how this cutoff energy, we must prove that their convergence. And yesterday, there already a lot of discussion, because if you do mean field calculation, you always end up with a ground state protein, or local minimum, right? So in order to make sure that you have correct ground states, normally a constrained calculation is necessary. How to do that? So you put in a Lagrangian multiply, and then you see, for example, this is we constrain that with quadruple deformation. We put the terms here, then gradually we can get the solution for all the deformation. Then in such a way, we can make sure we found the ground state properties. So the first application we made is that, for example, after we complete the code, so what should we do? Top important thing is that we should find some deformed halo, because that is the motivation why we spend so much time to develop the code. So we search for this net nuclear near the triple line. Finally, we found one example. That is magnesium 44. Magnesium 44. We found that the magnesium 44 is a good candidate for deformed halo. You could see here, this is the density distribution, right? And this is a neutron, and this is a proton, and this is in logarithm scale, and this is in normal scale. So this nuclear is found to be prolate deformed. And also there is a large spatial neutron distribution compared with the protons. Yeah. From theory is much easier to define, because we define that in such a way, we focus the size. We could see the size bigger. Secondly, we will examine which orbital contribute to that. Yeah. Then if it's no air orbitals, that's a small centrifugal barrier, then you could see the density decrease very far. But if the orbit is with large orbital angular momentum, the density is constrained by some kind of centrifugal barrier. So we call that kind of thing as skin. Yeah. So you see here, then we go to, that is how we look into these orbitals. For example, which orbital respond to the large distribution for magnesium 44, and because what we are doing is this. We expanded the deformed single particle orbiter by spherical components. So we can easily see which orbiter or what components contribute to the part. And then you see this is how we separated the core and the halo part. A big surprise, we found that the core is plurally deformed, but the halo part is oblate. Then we found something interesting. Number one, we found that the deformed halo does exist in microscopic approach. Secondly, for the deformed case, you may expecting that the core and the halo part might have different deformation, right? So this seems to be working fine. So if you remember yesterday, I mentioned to you about this functional PCPK1. So you see this is with a non-even mass, even nucleus with that mass measured. So we examine, for example, compared with other relativistic density functional, how this PCPK1 performs. For example, you see this DPC1, TM1, DDME delta, and DDME2 and NR3 star. All of these functionals. So you could see that the PCPK1 work well to describe the so-called the bending energy. So then we see what can we do. We just see how good, this is bending energy. And also we see, okay, how good they describe for example, for the spherical nucleus. You see, this for calcium, tin, night, and nickel isotope chain. So you will see this is the PCPK1 almost in this shaded area, right? This is N equal 20, 20, 20, 50, 82, and 126 isotope chain. Again, they are almost in the middle. And then we can also go to the so-called the deformed case, right? For the deformed case, this is bending energy. We are here also in this shaded area. This is ytterbium isotope. This is uranium isotope chain, right? And this is how they describe the deformation. Therefore, we trust that maybe the PCPK1 functional is good functional to describe the global properties. And we also have this the approach to describe the deformation in the nuclear in the neutron near the neutron trip line. Therefore, the combination of this approach with PCPK1 could be extended to describe the whole nuclear in the nuclear chart. In particularly, we can also get a confidence by examining the predicted power of the PCPK1. For example, you see this is a 53 new mass measurement performed on the GSI. Because they did the experiment after all this mass model has been developed. So it's very good that we could check how well, this model describes the newly measured mass to check the predicted power. So you could see that here is the PCPK1 works quite well. And then you see this TMY FRDM, which you maybe Nicolas call it micmac model, this HFB1. So you could see we are almost the same accuracy with the phenomenological model. We can also, for example, recently we also found another check with a unique combination of the atomic data. And then for this super heavy mass region, you see this is all description, quite satisfactory for the mass number from 200 something to 300. And then if you see WS4 and FRDM, you see their predictable is lost, but for us still remain. Therefore, we build up a collaboration group. Maybe you are surprised because normally there are always a big experimental collaboration group. The collaboration group for theory is not that common, but we are encouraged by the PRC editor office. They told us that they encouraging also theoretical collaboration. And we also found that, for example, with the nuclear theory, become more and more difficult. And also it become more and more resources demanding. It's a good idea to combine all this kind of group together to make the best use of the resources. So essentially, we're collecting something like 31 institutes from China, Japan, Korea, and then we all aim to build up a mass table with continuum and deformation included. We already achieved something. For example, this is our first paper with this name, DIBC mass table collaboration, because we give up all the strategy to perform a large-scale calculation, not that easy. So we test all the numerical program, and even that all this group we organized one online discussion every month, and every year we have twice per year workshop to collecting the people together for discussion. And then finally, we published the first paper for even mass nuclears. From totally, there's more than 2,500 nuclear for even nuclear. And then we want to study the full nuclear chart in 3 steps. First step is even nuclear. The second step is even the old N nuclear. And then the third step is a full nuclear chart. So you will see we already found something interesting. This is a full nuclear chart. Then you will see in this area, we really found some stability line or stability beyond the neutron zip line. This is interesting because easy to understand. Because you see beyond the 1 neutron zip line, we can also have 2 neutron. So we could have 2 neutron stable nuclear. If beyond this 2 neutron separation energy, or beyond the 2 neutron zip line, we may expecting also some, multi-neutron separation stable nuclear. So you could see that is the case. We found that this nuclear are still stable, even though the 2 neutron zip line ended here. And then, of course, these nuclei are stable because of the deformation. Due to the deformation change, without the deformation, there's no such phenomenon. So the continuum and also the deformation really make something very interesting. And then next step is that we already studied the old mass nuclear, and then is the even the old neutron nuclear calculation we already studied. It's not that easy. I just show you one figure here, how difficult it is. Because for a self-consistent calculation, you have all the neutrons. This all the neutron should have broken effects. And then if you have a deformation, changing with the deformation, the blocking orbit could be depending on the deformation. Because the change with the deformation, the single particle number also changes. So which orbital to block is a good question. So you have to try several try to find the correct orbital to be concerned. And secondly, for the odd nuclear, because if you have a different blocking, you could find a lot of knockout minimum. This knockout minimum is not necessarily the ground states. So what can you do? What you should do is to do a constraint calculation. For example, here I just show you an example for this nuclear. For this even nuclear, you studied the constraint calculation. And then you found the potential energy curve. From the potential energy curve, you can decide which one is really the ground states. And then go to next one, the dotted line, that is the case for all the mass nuclear. So you have one nuclear should be blocked somewhere. And then we found that we to always ask all the nuclear to occupy different orbit in order to search for the really the null communism. Then we found that the potential energy curve here is close to the even one. That sounds reasonable. And then it's also give us the information which one is the so-called the ground state. And then we can continue you see, this is for the neon-dium isotope chain. So from the proton triplet to the neutron triplet, how we search for the ground state. Then in such a way, we could see we get the correct bending energy, correct deformation, correct reading. And then we can compare with data. For example, here is the quadrupole moment. And the experimental value is represented by the Sonic square. And then you could see how the deformation changes with the Newton number. Then you will find that there is big jump here, right? There is a big jump here. This big jump here always corresponding to the shape coexistence. For example, for this nuclear, there are always two minimum in the energy curve. And then these two minimum could be computed with each other in such a way, and one nuclear may be product one. But go to the next isotope might be the oblate ones. Therefore, you could see this is the fluctuation here, which suggested the existence of shape coexistence. And apart from that, I should say in this collaboration is very successful because there are some young students coming and finally they produce a lot of paper. And then we can also go along this line. For example, one student where he is working for this case of deformed halo, he studied to develop the approach for so-called the halo interactionally deformed nuclei. Experimentally, they have no way to do that. So they have to do some kind of, excitation measurement. And for example, if they measure the giant resonance or something like that, they could use two bump corresponding to the either non-X or the short X. Otherwise, it's difficult, right? And this is the triaxial nuclear case. For example, in this nuclear, he could find how the core part and the halo part, the density division look like. And then he can also calculate the, for example, the deformation, the root mean square redo, for the core and also for the halo. And then you see this is using this parameter schematically, he could show how the core look like and also for the halo look like. And this is a parameter for the core. You see, the ready for the core is about 3.8 Fermi. For the halo is about 5.26 Fermi. And the quadruple deformation is 3.38, which is so to say well deformed. And for the halo part is 0.8, that is really super deformed. And this is gamma equal 50 degrees, and this is gamma equal minus 23 degrees. So that could tell us that is the case for the deformation. And of course, using this approach, we can, for example, when we're building up this nuclear chart with deformation and continuum effects taken into account, we not only provided the root mean square, radii, mass, or the ground property, and using the single particle levels, we can also build up, for example, the energy level density, which is quite useful in the future for the rapid neutron capture process calculation, in particular for this neutron-rich nuclear. So, so maybe there are also some calculation, for example, we can also apply this for super heavy. For example, there are quite a bigger discussion. You know, for example, what would be the next magic number for magic number for super heavy? Yeah, this is super heavy of stability line as island is a huge attraction for the experimentalist. So we have performed huge calculation, so to say, from 100 to 140 for the atomic number and also this neutron number to see where is the magic number. And finally, you will see we found that 120 and this number could be the possible magic number. And then this is also the stability line, but this is available experimental data. So far, the experimental information is only concentrated on the neutron deficient case. And then for the super, for example, for the super heavy 120, you see, without the deformation, you will see you have the minimum here, right? Then one should really be careful about, for example, this is without the quantum effect. If you are talking about liquid drop or something like that, it's not stable. But with shear effect, you have this, you can have energy minimum here. So therefore, that is the magic number from the potential energy surface. We could see that is the next magic nuclear should look like. And then one question comes, why this minimum survives? If you take into account, for example, the reflection asymmetry, so in order to do that, we must develop the code which allow the reflection symmetry is broken. We are very fortunate. For example, we found in such case, The ground state exists, but the second minimum almost disappears. And then in this nuclear, you could see after you including the reflection and symmetry breaking, and this minimum doesn't exist anymore, but still we have a chance that this kind of super heavy nuclear could still exist. And another thing is that, for example, this constrained concretion is also very useful in determining this fission barrier. For example, this is the famous plutonium-240. And this is the ground state, this is inner barrier, this is second minima, and then this is the very complicated relativistic density functional calculations. And nicely, you see this is energy surface look like. If you allow different triaxial deformation and also reflections, octuple degree of freedom. So this is the potential energy surface looks like. And then finally, you see this is the result how the theoretical calculation could reproduce. For example, if with not broken the actual symmetry calculation, then you will find this we cannot reproduce inner barrier. And also the out barrier is very high, but after we included the triaxial degree of freedom, the inner barrier and outer barrier height are reasonably reproduced. And also after you take breaking the reflection symmetry, then you see this, you could see this barrier is also reproduced so well. So this is essentially the ground state calculation, and I hope that you could see that the relativistic density functional can really do a lot of sense. I suppose tomorrow, for this extra time, maybe we put our priority on your question first. After your question has been discussed, then if we have time, I show you some example of excited states and also what about the future. Future is more important. Okay. Oh, yeah, okay. Okay, okay, good. Okay, so thank you very much.